Hey everybody, I'm going to give you guys a quick lesson on binary, right? So first off, why do computers use binary, right? It's very easy to have a state in a circuit that is either 0 or 1, right? And usually that's between the power supply. Sometimes it's called VDD, which is voltage drain, or VCC, which is voltage collector. Those are named after pins on a transistor. None of that's important. Pretty much high voltage is a 1, low voltage is a 0. Now, what defines a high voltage or a low voltage depends on the electrical specs. But the great thing about digital is once you've digitized it, you really don't care about the electrical circuit, right? It gets you away from the physical electrical realm of whatever's going on and keeps you to a pure information realm where software can do its job and you can just do the math, right? So we're going to talk a little bit about binary logic. All right, today's lesson on binary logic is truth tables, right? So binary is coupled with some very simple operations that are logical in nature. Now what that means is that you say, if I have one number and another number, what does that mean? What is the result of some logic on those numbers? For example, you have, I'm going to strain on here. This is a mouse. My first time. Give a break. So and. So on and, both A and B for C to be true. Right. Now I could write that out, but it's a lot easier just to put it in a truth table, right? So we have A, we have B. These just represent two different binary numbers, okay? So A can be a 0 or a 1, and B can be a 0 or a 1. I'll just put a vertical line here. C is the output of that, right? And it equals A. Let's see if I can do an ampersand in this. There we go, just like on the cereal box. Okay, A and B, right? So C is equal to A and B. Well, let's go ahead and put all the possibilities, because I said A can be either a 0 or 1. Same thing with B. We're just going to put all the different possibilities. And those possibilities are 0, 0, 0, 1, 1, 1, and 1, 0 for A and B respectively. Okay? Now, the logic here is that C is only true if A and B are both true. So you just go down the pipe here, and you see the only time where A and B are both true is this case. Remember, 1 represents true, 0 represents false. All right? Not too bad, right? So this is called a truth table. All right? Truth table. Now, there are lots of other operations. One of the other operations is an OR. So for OR, C equals true if A or B is true. All right. So A and B, we're going to do the truth table again. Okay. Now we're going to give a different symbol because there's not a symbol for OR that you know of, right? Necessarily. It's going to be called the pipe symbol. It's the keyboard on your key. If you look at the backslash key and you press shift, it's this vertical line, so it looks like this. And it's a little taller than the letters are. So that's how you kind of know it's not an I or an L, a lowercase l or something like that, right? So here's A or B. All right? So let's go through our possibilities again. Now, this left side of the truth table is always the same no matter what, because it's just every possible combination of A and B, digitally speaking. So if A or B is true, then C is true. Well, A or B is not true in the first case. That's a 0. It's a big zilch. Here, it looks like B is true, so that looks like it's true. Now, this next one is interesting because we have both A and B is true, right? But it said if A or B is true, then the output's true, right? So it's A or B. Doesn't mean it has to be exclusive. There is an operation that is an exclusive OR, but this one is not it, right? Perfect. Wonderful. So there's our truth table for A or B. Now there's a few things I want you to note, okay? Back on this and, this is going to be really important because I'm going to take you on a journey through embedded programming, and Bitwise Logic, which is something I'm going to show you guys next time, is really important. I want you to note something. So note, if B equals 0, then C is equal to A. Or, sorry, is equal to 0, right? So if B is 0, if for the AND operation, if B is 0, then the output is going to always be 0. So here's B 0 and B is 0. And notice how both the outputs are 0. Okay? Now, if B equals 1, C, now this is kind of cool. Let's take a look at what happens when C equals 1. When C equals 1, we have A is 0, B is 1, C is 0. When A is 1, sorry, over here. When A is 1 and B is 1, then the output C is equal to 1. But you see how, and I'll do this in blue here. See how this is equal to that? That means that by this logic, C is equal to A if B is equal to 1. This is really important because if you have this AND operation, you can use, if you AND something with a 0, I call it annihilate it, you destroy it, right? It's the great destroyer. If you AND it with a 1, you preserve it. So I'm going to put on here destroy. I use aggressive language because I'm a boy. That's how we boys do. And if, there we go, preserve. This handwriting is only slightly worse than my real life handwriting. All right. Let me see if there's a way I can add a page or something like that. All right. My first time using it. Add note, add text, add active pen. I might have to cut this part of the video out. Can I just add a page to this? All right, so we're just going to continue the binary logic I finally found. I'm just going to make a new whiteboard. I don't know how to make a new page in here just yet. I mean, this kind of looks like a new page note here, but all right. So we got another operation really quick to do. This one's actually going to be pretty easy. Okay, so this one's the not. The not, right? It's, you know that old, it's a really dumb joke. There's a pretty funny scene in Borat where he explains the not joke, but what you do is, it's just, if you say A is equal to B, not, right? So it only works on one, you only work on one thing, right? A, so here's our A, that looks kind of like the Blair Witch symbol. Whatever, close enough. 0 and 1. The not symbol, which is for binary logic, or sorry, bitwise logic, is this little tilde key. If you look at the single apostrophe symbol, the one next to your 1 key, hold shift. The tilde is a little curvy thing. Okay. This is repugnant. Let me just fix that. All right, cool. Now we've got a truth table. Easiest truth table in the world. So imagine I just say like A is equal to 0, not, right? Or A is equal to 1, not, right? Not is just opposite. It just means opposite. It's just opposite. It's really, really easy. Okay. Oh, sorry, I went to the next operation. I need to go and finish back up here, right? So, because there's more to say about this. All right, now that I've introduced them, jumping a little bit out of order. You can tell that I just make this stuff up as I go along, but we're not too far off track, so bear with me. All right, so next one, note. Okay. Pause the video as soon as I snap my fingers, okay? Ask yourself this. If B is equal to 1, then C is equal to what? Huh? All right, did you get it? Okay. This means it's equal to 1. If you OR anything with 1, it turns into 1. Okay? And I'll give that a name that's pretty cute in a second as soon as I think of one. Now, if B is equal to 0, all right, then C is equal to. You're going to feel a little bit of a pattern here. Ready to answer it? Pause this. Pause the video once I snap my fingers. All right. Because you're a hardworking person, I know you did it. C is just equal to A. Right? So when B is 0, C is just equal to A. Just like it was before. Except this time we're a little bit flipped, right? Now when B is equal to 1, anything ORed with a 1 is going to be a 1, right? See? Perfect. And I'm going to give this a cute name. This one is going to be the preserve, yet again. So we're going to preserve. Cool, cool, cool. All right, and this one, you destroy, we could just say create. That doesn't feel very creative, right? Let's call it the set. And you know what? We can call this destroy if we want to be a little more technically correct. Reset. Okay? When you're in the technical world, we're actually going to say these things. When you set it, it's like you set it up on a shelf. When you reset, it's like you take it back down. But when you reset something, that usually means send it back to logic 0. All right, perfect. Okay, let's do some bitwise. All right, so now that we've done that, let's do a little bit of bitwise logic. Now, what does that mean? All bitwise logic is when you have binary logic and you're doing it lots of times, okay? I'm going to use blue. I like blue. Blue's cool. Me and blue are friends. All right. So let's say I have a number, A. Okay. Now, in bitwise logic, we have multiple digits. All right. So multi-digits. All right. So we got multiple digits of binary. All right, I have to get good at the stylus pen. This mouse ain't cutting it. That's okay. Thanks for bearing with me. All right, so let's say A just equals 0, 1, 1, 0. And I'm going to cluster these in sections of 4, so 4 digits at a time. Let's say this is an old computer. Let's say it's an old 8-bit computer. And this number just happens to be A equals 0, 1, 1, 0, 1, 1, 1, 0. Okay? That's the binary. All right? Now let's do B is equal to... Let's do a 1, 0, 1, 0, 0, 0, 1, 1. Yeah, why not? Just making these numbers up at a time. Okay, so the answer is now, what is A or B? All right, now the way that bitwise logic works is that you're going to go down each column here and just apply the logical operator, right? So this is an OR. So, okay, if either of these is true, then the output is true. So A and B, right? Okay, so A or B, right? So this is a 1 because 0 or 1 is a 1. Okay, next one is a 1. Let's do this really quick. 0 and 0. If you OR those, you get a big old fat 0. All right, cool. Let's do something more exciting, right? Let's do an AND. And the exciting part is I got to draw an ampersand. Oh, clutch it. Okay. My carpal tunnel's coming right back. All right. Remember, we're doing A and B here. Okay? So don't get too confused. There's this column right here. This row right here. All right. So A and B. So 0 and 1. The output's going to be 0. Remember. All right. 1 and 0. The output is 0. Yet again. All right. 1 and 1. Oh, the output is 1. Very cool. All right. 0 and 0. The output is 0. Neither of them are even true. Let's do this really quickly. Remember that a 0 is going to destroy you or reset you if you are ANDing with the 0, okay? All right, there we go. Perfection. That is pretty much how bitwise logic works. You just go down digit by digit. Now, I chose 8 bits, but you can be any number of bits. The number of bits is the number of these digits. If you want to do 64-bit, you can. Modern processors run at 64-bit. What we're going to program in here is not modern processors, or are not modern processors. They're going to be more like they're going to be more like Atari processors, right? These are embedded chips. They're tiny little chips that go on our circuits. As you learn through these videos, you're going to learn how to program those chips. Okay. So where do we want to go next? Let's do a little more complication. Okay. we're going to use our NOT operator, right? A and B. Now the cool thing is we don't have to strain our eyes because all we have to do is look one row up and we know what A and B is, right? And they're inside this parentheses, so order of operations do apply. So we're going to do the A and B first, which luckily we've already done. Now we're going to NOT it. What we do when we do a bitwise NOT is we're just going to make every single digit of this number just the opposite of its previous state. A lot of words, pretty much all the zeros go to ones, all the ones go to zeros. So it's like the revelations of bits, you know? The bitwise ultimatum. All right, here we go. Boom. All I did was just opposite, 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 opposite. 8 times. Perfect. All right, let's learn something new. Let's make another one and another one. Okay, let's learn to shift. Oh. Wait, you could just move around on this? Oh, okay. That's a game changer. All right. I've got a little less stupid, everybody. Let's learn how to shift. All right. What this means is move A by B bits. Okay. So there's 2 types, and I'm going to use my blue pen. There's the right shift. Okay. Boop, 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 boop. Notice there are 2 of them. Little single quotes around it. Notice there are 2 of them right there. Those are the 2 angle brackets. That's if you hold shift and press your comma or period key, that's what you're going to get. Or sorry, that one in particular is the period key if you hold shift. So if you use this, what it looks like is, I will use green. How about that for examples? I'm going to have a color code. That seems like the cool thing to do. Let's say A right shifted by B. Okay. All right, so let's do, how about do 0, 0, 1, 1, 0, 1, 0, 1. Okay, this is going to be an interesting one. And I want to right shift it by, let's say, just the number 2, right? Now, keep in mind that this is binary, right? We haven't even told you what the binary numbers mean. Just don't even worry about what actual numbers they are. I'll do a separate lesson on how to read binary. And this one is just decimal, right? So these are the Arabic numerals you're used to. Okay. All right, so what's going to happen is this is going to do one of these numbers. It's going to move to the right by 2 spaces, so you're going to see it go chunk, chunk. All right. I wonder if I can even take the lasso tool, but I just got to use your mind's eye for this one. It's going to chunk everything to the right by 2 digits. So I'm going to start from the rightmost digit, 1, 0, 1, 1, 0. And now, because we have digits that aren't here, everything that's outside of what's shown here is assumed to be 0. So these 2 new digits, these guys are new. And these guys on the right, notice how they're not there anymore, right? They fell off. Cool. All right, so these digits, the zeros are new, and the ones on the right fell off. All right. Last thing I'm going to show you guys how to do is just do the left shift operator, but it's exactly the same. So left, the symbol for that is just the other way. Okay. Let's say the number is, let's just do the same number, 0, 0, 1, 1, 0, 1, 0, 1, and I want to left shift it, blippity bloppity. Let's do 3. 3 seems like a fun number. All right, so we're gonna left shift this by 3. So 1, so you're gonna see, actually let me Control Z that. We're gonna do a 1, 2, 3. Right? So this 1's going to go away. If you go out of the bounds, you're gone, right? That's how it works. Okay, so that's going to mean 1, 0, 1, 0, 1, 0, 0, 0. So this guy right here. These guys fell off. And these guys are new. All the new guys are assumed to be zeros. That's kind of that's sort of a statement on newbie culture. All right. We've done two things in Bitwise Logic. Yeah, I think, I'll tell you what, I'm going to go ahead and put some examples, problems, down in the description, right? And you guys can do them at your leisure. I'll just link to a Google Doc or something, and then finish them, and I'll put an answer key as well in the same Google Doc location. So I'll give you the problems, and I'll give you the answer key, and you can get some good practice. If you have any questions or anything, feel free to contact me. I'm at thealexmanassa.com. The link will be in the description, which I really need to make sure I put in there. And yeah, enjoy. I hope you enjoyed this. This is going to get you on your way to learning how to do embedded development. There's only a few skills necessary to do embedded development. This is like one of them, and there's like 5 I counted total. But I'm going to be doing these fairly often. This was like no problem. It took me 20 minutes to do this little quick thing. And I'm just going to keep rattling these things off, and I'm going to link them, and I'm going to have a structure for how this works, okay? I want to thank you guys for sticking around. I hope you learned something, and I hope you get a little bit better at engineering every day. All right, this has been the Alex Manassa, and I will see you next time.